So one of the most interesting part of geometric representation of a wave function is the Bloch sphere. Or actually it's maybe the most interesting part of this video, that you find the Bloch sphere in many contexts of quantum information theory. It gives us very visual representation for single qubit operation or single qubit representation. So the Bloch sphere is characterized by angles. So if I have the 0 on 1 applied here, the 0 on the z, and the 1 is in the minus z. It's kind of spin up or spin up and spin down, spin up and spin down for the z and minus z. So I take a wave function and write it like this. This is the Bloch sphere representation. What about this exponential? This is called global phase. So this global phase can be neglected because it's kind of negligible in our representation in the Bloch representation, but it's just global and it can act over this kind of wave function, and it does nothing. So I can write down the 0 by cosine theta over 2. So you can find that this is a wave function here, and if it's its projection over the plane of xy here, that you have phi between the x and its projection, and I'll have the theta for its kind of the wave function at psi with the z, and I can write down that by cosine theta over 2 0 plus sine theta over 2, and this exponential is very important exponential for our phase representation for this geometric representation of the wave function. So this gives me kind of condition for the theta. Theta can vary here from 0 to pi, okay, and this is for the latitude, and phi, it can vary from 0 to 2 pi for the longitudinal action here. So maybe if you look at the 0, that's kind of this x, if I would like to write down the wave function here, it gets me that phi is 0, so this can be cosine theta, which is 90 degrees over 2, is 1 over square root 2, so it can give me 1 over square root 2 for 0 and for 1. What about y? So cosine theta is the same, sine theta is the same, but phi is now 90 degrees. So 90 degrees means that I have sine cosine 0 plus I, so here the wave function can be 0 plus I 1 and all 4 over square root 2, right? Okay, so I can write down the 0 for, if I have the representation for 0 here. I try just to make sure that you capture the essence of the Bloch sphere. If I have the 0 operation, sorry, the 0 ket, the 0 wave function at the z, so the 0 here means that I'm applied on z, so it means that theta is 0, so cosine 0 over 2, so cosine 0 is here just 1, and you can find that can be neglected here because sine 0 is 0 and 0 is 0. Just reaching from this expression, I'll try just to reach from this expression and landing over the 0 on the z. It's just nothing else than a spin up, for example. So what about superposition of the 0 on 1? So you can write down here the cosine theta, okay, this for x, which means that I have 90 degrees over 2, this is 45 degrees, and it can be kind of this expression, and this is for x. So you have also rotation matrices, and rotation matrices are important in the context of the ground state and the excited state of rotation around the x, maybe the y and the z, corresponding to each theta with its operation. They can be written as exponential minus and each corresponding Cartesian operation, Cartesian x, y, z, and these unitary or just kind of rotation matrices can be written as u is equivalent to this rotation for z, for y, for x. And by this way, you capture the essence of rotation matrices, all operations or the necessary operations to build or start to build a quantum circuit and trace out all these kind of wave functions and try to see the result or the outcomes.